In this lecture, we're going to look at some more interesting and more in-depth logical equivalences, starting off with De Morgan's laws in logic. So you'll remember that when we studied set theory, we proved some things called De Morgan's laws, and those were to do with complements and unions and intersections. For example, we proved that if you had two sets A and B, which were subsets of some big set omega, and you looked at the complement of A union B in omega, then that was equal to the complement of A intersected with the complement of C. So now if you take union and you make it into or, and if you take intersection and make it into and complement and turn it into not, then what you get is some logical laws, so logical equivalences, called De Morgan's laws in logic. And here they are. To state them formally, if you have two well-formed formulas, phi and psi, then, first of all, the negation of phi or psi is logically equivalent to the negation of phi and the negation of psi. And secondly, if you take the negation of phi and psi, then that's logically equivalent to the negation of phi or the negation of psi. So how do we prove this? Well, you will remember the meaning of a logical equivalence. The meaning of saying that two formulas are logically equivalent is saying that a truth assignment makes one of them true if and only if it makes the other one true. So we have to check that under any truth assignment at all, the left-hand side of, for example, this equivalence takes the same truth value as the right-hand side. So how can we do that? Well, what we'll do is we'll make the observation that any truth assignment at all either makes phi and psi both true, or it makes phi true and psi false, or the other way around, or it could make them both false. And we just need to check that in any of those four cases, the truth assignment gives the same truth value to the left-hand side of my proposed equivalence as it does to the right-hand side of my proposed equivalence. So we're just going to check the first of De Morgan's laws. The second can be done in a similar way. So we're going to think one row of this truth table at a time. What truth value do we get for these two formulas heading the right-hand columns of my truth table? So we'll suppose first of all that we have a truth assignment which gives both phi and psi the value true. Well, in that case, phi or psi is true, so the negation of phi or psi will be given the value false. On the other hand, the negation of phi will be false and the negation of psi will be false, so certainly the negation of phi and the negation of psi will be given the value false. And you can see that in this case, in the first of our four cases, the two formulas were given the same truth value. They were both false. The next case is what happens when phi is true and psi is false. Well, in that case, phi or psi will be true because at least one of them was true, so the negation will be false. And on the other hand, the negation of phi will be false because phi was true, so that and anything will be false. So again, they have the same truth value, they're both false. And our third case, when phi is false and psi is true, well, for the same reasons, these things will both be false. But finally, if we look at the last row here of our truth table, when both phi and psi are false, well then phi or psi would be false, so its negation would be true. And looking at our second formula, not phi will be true, not psi will be true, so not phi and not psi will be true. In every one of these possibilities, the two formulas had the same truth value. So for any truth assignment whatsoever, the two formulas, not phi or psi and not phi and not psi, got the same truth value, and therefore those formulas are logically equivalent. So that proves the first of the two logical equivalences known as De Morgan's laws. To do the second one, you just need to do the same thing. So create a truth table the same way. we're now going to look at a different logical equivalence, which is a logical equivalence which allows us to express implies in terms of other connectives. So specifically, we'll show that if you have any two well-formed formulas, phi and psi, then phi implies psi is logically equivalent to not phi or psi. And again, what I've written in this logical equivalence is not strictly speaking a well-formed formula, so there should be an extra set of brackets there, but we're going to continue to omit brackets when the formula you get by omitting those brackets is still unambiguous and is a little bit clearer. So it's a little bit clearer when we omit brackets because it makes things a little less messy. And again, the meaning of logical equivalence is that the two formulas are true under exactly the same sets of truth assignments. So if you take any truth assignment at all, then it gives the same truth value to phi implies psi as it does to not phi or psi. So we just make the observation that given any truth assignment at all, well, either it makes phi true and psi true, or it makes phi true and psi false, or the other way around, or it makes them both false. And we're just going to check that in any of those four cases, the truth values given to our two formulas are the same. So working out one of this first empty column is easy because that just comes directly from the truth table for implies. And you'll remember that implies was always true, except in the case where the thing on the left was true and the thing on the right was false. So that's the truth table for implies. And now we have to think about our final column, and we have to think let's think about when could this final column be false. So the only way for an or statement to be false is when both of the things in the or statement were false. So this can only be false when psi is false and when not phi is false. In other words, when phi is true and when psi is false. So the only time this will ever have false is in this row of the truth table when phi was false so that not phi, so phi was true so that not phi was false, and when psi was false. And in all other cases it will be true. So you can see that in every one of the four cases the two formulas get assigned the same truth value. And that means that the two formulas are logically equivalent because they have the same truth value no matter what truth assignment we use for their propositional variables. So the reason to be interested in this particular logical equivalence is that when I introduced connectives to begin with, we said that actually we only needed those four connectives. You know, there are other connectives, but we don't actually need them to express any logical formula we want. And I said, in fact, we don't even need all of the four connectives and or not implies because we can eliminate some of them. And you can see that what this logical equivalence would allow you to do would be to take a formula which had implies in it and get rid of the implies and produce a logically equivalent formula which didn't use implies. Because what this shows you is that every time you see a well-formed formula containing implies, you can replace phi implies psi by not phi or psi, and thereby you can obtain a logically equivalent formula that doesn't use implies. So this is telling you that strictly speaking you don't need the connective implies. If you only care about well-formed formulas up to logical equivalence, then you can eliminate implies from any such well-formed formula by replacing it using this logical equivalence. Okay, next logical equivalence is about a thing called the contrapositive. So the contrapositive of a logical statement of the form A implies B is not B implies not A. And what our theorem here says is that any implies statement is actually logically equivalent to its contrapositive. Specifically, if you have any two well-formed formulas, phi and psi, then phi implies psi is logically equivalent to not phi implies not... Let's say this again. Then phi implies psi is logically equivalent to not psi implies not phi. And this is one of the logical equivalents that's really useful when you're doing a proof. Because if you're trying to prove a statement of the form something implies something else, then it can often be easier to prove the contrapositive. And the contrapositive is sometimes, as I say, sometimes easier to do. So if you want some specific examples, then take a look at the typed lecture notes for this part of 0005. You'll find a link to some examples where it's easier to prove the contrapositive of a statement than it is to prove the statement itself. So if you want to prove this logical equivalence, well, you can do it if you want the same way that we've done all of our previous logical equivalences, by taking an arbitrary truth assignment, noting that it either gives the value true or false to phi and it either gives the value true or false to psi, and checking that in each of those cases it gives the same truth value to phi implies psi as it does to not psi implies not phi. But we're going to do this a different way. We're going to do this in a way which is similar to the kind of algebraic manipulations that you do when you're manipulating ordinary equations to do with numbers. So we're going to step through this proof line by line. Here is the first line. In the first line, we use the logical equivalence that we proved on the previous slide to say that phi implies psi is logically equivalent to not phi or psi. That's precisely the logical equivalence that we did on the previous line. Then we can use the commutativity property for or. We saw this in our last lecture. A or B is logically equivalent to B or A. So I can use that to swap the order of the two things on the previous line. Next, we use double negation. Again, in the previous video, we saw that not psi was logically equivalent to psi. So I'm simply going to replace psi by not psi, and then I'll have a logical equivalence. And you'll remember that property was called double negation. Okay, finally, let's just use the logical equivalence from the previous slide again, and notice that this is not something or something else. And that is always logically equivalent to something implies something else. So when you have not psi or not phi, that's logically equivalent by the logical equivalence on the previous slide to not psi implies not phi. So we're done. We started off with phi implies psi, and by using a sequence of logical equivalences, we've ended up with its contrapositive, not psi implies not phi. Okay, our final theorem then, our final logical equivalences, which I'm not going to prove but just write down, are the following. If you take any three well-formed formulas, phi and psi and theta, then you have this distributivity property, which is, well, in fact, two distributivity properties. The first one says that phi and psi or theta is logically equivalent to phi and psi or phi and theta, and that should remind you of the distributivity properties that we had for sets. So for example, we saw that if you have any three sets A, B and C, then A intersect B union C was equal to A intersect B union A intersect C. So if you swap unions for if you swap unions for ors and intersections for ands, then what you get is precisely this logical equivalence that we've got at the start there. And similarly, there's a logical equivalence with the ors and the ands swapped over. Phi or psi and theta is logically equivalent to phi or psi and phi or theta. And that comes that looks just like the other distributivity law which we proved for sets. So I'm not going to give a proof of this. If you'd like to do so, then what you can do is write out truth tables showing that under any truth assignment whatsoever, the formula on the left and the formula on the right is given the same truth value, which means that these expressions are logically equivalent.